Alright, today I'm going to be going over 5.5, and our objectives for today are to explain and describe how to solve quadratic equations that have imaginary roots. And so our new vocab is going to be imaginary numbers, and complex conjugates. So an imaginary number. They came into play when they had to start taking square roots of like negative numbers, like the square root of negative 25. Well, if you remember the square root of 25 is either 5 or negative 5, because 5 squared gives me 25, and negative 5 squared also gives me 25. But the square root of negative 25, remember square root says a number times itself. Well, there's no two numbers that 5 times 5 gives me 25, and negative 5 times negative 5 gives me 25, so I can't get that negative 25. So they had to come up with some way to deal with that, because in some places, especially in the sciences, you can run into where you have to take the square roots of negative numbers. And so how they handled that was they came up with what's called the imaginary unit. And that's just that we're going to let I equal the square root of negative 1. So now we can deal with this because we can rewrite this as the square root of positive 25. The square root of 25 times the square root of negative 1. And we already know that the square root of 25 is plus or minus 5. And now we have that the square root of 5, the square root of negative 1 is equal to I. And so we just simply handle it like that. Now also on this assignment, you're going to have to be able to reduce square roots. And when you reduce square roots, we basically have three rules. The first rule is that we leave no perfect squares under radical sign or inside the radical. So that would be like the square root of 72. What we're going to do is we're going to break that 72 up into a perfect square that goes into 72. So it's helpful if you know your perfect squares, like 1 squared is 1, 2 squared is 4, 9, 16, 25, 36, 49, 64, 81, 100. We could go to 121, 144, 169, 196, and 15 times 15 is 225. You won't need anything bigger than that, I don't think, on any of the assignments. But you have to look and say, okay, what's the biggest perfect square that goes into 72? There's a couple ways you can do it. You can go through and say, well, what number's going, like 9 goes into 72 8 times. So the book would do it this way. They would write it as the square root of 9 times the square root of 8. But the square root of 8 has a 4 in it, and 4 is a perfect square. So I can break that into 9 times the square root of 4 times the square root of 2. Now the square root of 9 is 3, the square root of 4 is 2, and we can't take the square root of 2, so we have that. And so now we have that this equals 6 times the square root of 2. The way I do it is I just put it above there. So in this case, I would say, well, 72, I know that 36 goes into it. Now if you do the 9 times 4, the thing to realize is a perfect square times a perfect square gives you a bigger perfect square. So 9 times 4 is 36. So I can break this into 36 times 2, which gives me 6 square root of 2, and that's plus or minus. Now, if that had an I in it, or excuse me, not an I, but let's say it was a negative 72, then I would just bring out an I and write that as plus or minus 6I square root of 2. So that's the first case. If I have a radical that can be reduced. The second rule is leave no fractions under radical sign, or in the radical sign. So that would be, let's say I had the square root of 2/3. Well, that's easy to take care of rule 2. You just break it up into two parts. The square root of 2 over the square root of 3. And we've taken care of that case. But that causes a problem with our last rule that says no radicals in the denominator. So now it comes in, how do I take care of that square root of 3? I can't leave that down there in the denominator. And you should have learned this reducing in algebra, probably, and again, you saw it, I know, in geometry. So here's what we have to do. We have to get rid of that square root of 3. Now, the only thing you can multiply a number by and not change it is 1. So what we're going to do is we're going to take that square root of 2 over the square root of 3, and we're going to multiply it by the square root of 3 over the square root of 3. Because this is really only equal to 1. So it's going to change the way it looks, but not change the value. So when you multiply radicals, you multiply the numbers in front together. So 1 times 1 is 1. And then you multiply the numbers inside together. So we get the square root of 6. And then the square root of 3 times the square root of 3, that would be the square root of 9. But the square root of 9 is 3. So if you multiply a radical by itself, if it's a square root, it just becomes that number without the radical sign. And so that's how we can take care of reducing them. So we're going to be using these rules, and now we're going to apply it to negative numbers. Nothing changes. So let's take the square root of negative 5/4. Let's go 5/9. 5/7. Okay? So it's easy to take care of the negative sign. We just bring an I out front. And we can break it up into the square root of 5 over the square root of 7. And then to get rid of this, we just multiply by square root of 7 over square root of 7. So our final answer would be plus or minus I square root of 35, 5 times 7, and square root of 7 times square root of 7 would be 7. And we would be done with reducing that. Let's take another one. Let's take the square root of negative 75. Okay? So again, it's easy to take care of the negative sign. That's an I. Then I break this up. Perfect square that goes into 75 would be 25 times 3. The square root of 25, if you can take the square root, it comes out front. So plus or minus 5i. If I can't take the square root, it stays inside. So you'll be reducing those. Then, imaginary numbers. So, an imaginary number is the square root of a negative number. So the square root of negative 6. Alright? Imaginary numbers can be written as bi, where b is the real number and I is the imaginary unit. So in this case, it would become plus or minus I square root of 6. So in this case, our b would be 1, because there is no number here. If it was, let's do the square root of negative 36, then that would become plus or minus 6i. So b in this case would be 6. And the square of an imaginary number is the original negative number. So here's what it's talking about. If you square an imaginary number, if we square I, well, we already know that I is the square root of negative 1. So this is really that, and then the squared and the square root cancel, so you get negative 1. So if we had 3i and we squared the whole thing, 3 squared would be 9, I squared would be negative 1, so this is I squared, which would equal negative 9. So it's just some simplifying. But if you just get over the worrying about an imaginary unit, it's just if you have a negative sign, you bring an I out front, and you take care of that. So here's what happens as you take I. We already know that I is equal to the square root of negative 1. I squared, since the squared and the square root cancel, just gives us -1. I cubed would be the same as I squared times I. Well, since that's -1, -1 times I would give me -I. And I to the fourth is the same as I squared times I squared. And -1 times -1 is 1. Now, what happens is, what's I to the fifth going to be? Well, it's just 1 times another I, and so that's going to be I. So this pattern is going to continue to repeat. I to the sixth is going to be -1. I to the seventh is going to be -I. I to the eighth is going to be 1. And that pattern will continue. So what the book's going to do is they're going to ask you to find like I to the 67th power. Okay? Now, you don't want to make this chart all the way out to 67. So all you have to do is divide 67 and divide it by 4. Now, if you do that in your head, you might know that 4 goes into 64, and so I'd have 3 left over. The remainder is the power. So since this has a remainder of 3, this would equal -I. If you do it on a calculator, 67, and you just divide that by 4, you're going to get so you're going to get 16.75. If you have it as a decimal, if your decimal is 0.25, then it's simply I to the first power, so I. If your decimal is 0.5, then it's going to be -1. If it's 0.75, it's going to be -I. And if there is no decimal, it's 0, it's just a whole number, then your answer is going to be 1. So all you have to do is divide by 4, and that will help you, or give you the answer as you go through this. Now, a complex number. So a complex number, so we've had the real numbers, which is what we worked with most of your math with, and now we're adding the imaginary. Well, a complex number is just, it's part real and it's part imaginary. So A plus BI. Where A and B are both real numbers, but A is the real part of the complex number, and the BI is the imaginary part. So the question is, where does this come into play? Well, we've been completing the square, and so we're going to solve equations today, but now not all of our answers are going to be real numbers. So we're going to take a problem like, let's go x squared plus 6x plus 30. And we're going to find the roots. Now remember, zeros were where it crosses the x-axis, and that's where it's equal to 0. Well, the roots are when it equals 0, but they could be imaginary solutions. So as we go through this, the process becomes the same. We move the 30 to the other side. Then we take half of b. Half of 6 is 3, and 3 squared is 9. So we add 9 to both sides. Now we complete the square. So remember, to complete the square, it's the square root of this, x, the sign in the middle, plus, and the square root of 9 is 3. And then -21. So then to solve this, we're going to take the square root of both sides. So we're doing this. Now here's where we get the negative. So we just go I square root of 21. And then we subtract 3. So x equals -3 plus or minus I square root of 21. So if I wrote those as two separate answers, which you don't need to do, it would look like this. We'd have -3 plus I square root of 21 and -3 minus I square root of 21. So this leads into the next part because we have these two answers. It's what's called a complex conjugate. And a complex conjugate of a plus bi is simply a minus bi. All it's saying, because we have this plus or minus, we're going to end up with a, if you have one of your answers like this, the other answer has to be the conjugate of that, which is the same thing. You change the sign of the imaginary part. Now, it seems really easy. They're going to tell you, they're going to say like, one of your roots is 5 plus 6i, and they're going to ask you, what does your other root have to be? And as we look at this, the complex conjugate, if a quadratic equation with real coefficients has non-real roots, this is a non-real root, then those roots are complex conjugates. So if we have 1, we have to have its complex conjugate, which would be 5 minus 6i. Now, ways they can make this so you can make a mistake, they could go 3 minus 2i. Well, again, it's just the opposite, 3 plus 2i. But here's what else they'll do. They'll do maybe negative 2i plus 4. The tendency is everybody puts negative 2i minus 4. But you have to remember what changes is the imaginary part. The real part stays the same. So this would become 2i plus 4. Now, if it helps you, you can just always write it in the form to start with. So I can change this from here to there, and then it makes it, then you never make that mistake. You go ahead and put it that way. So, on the assignment, you're going to do a lot of work we've been doing on completing the squares. So let's take another look at one of those. So let's put a number in front. Let's go 4x squared plus 16x minus or plus 71. All right? So we set it equal to 0. We divide by 4 because we can't have that a in front. So x squared plus 4x equals negative 71 fourths. We complete the square. So that would be half of 4 is 2, and 2 squared is 4, so I have to add 4. Now when I add 4 here, I have to change it in fourths. So 1 times 4 is 4, so I multiply that and I get 16. And so we get a negative 55 fourths. So this becomes x plus 2 squared equals negative 55 fourths. Take the square root of both sides. So we get x plus 2 equals, plus or minus, to deal with that negative sign, I'm going to bring an I out front. There are no perfect squares in 55. So that would stay that way. And the square root of 4 is 2. And now we just subtract 2. And we have the answer. Now there's one other part of the assignment that you're going to have to do, and that is they're going to give you problems like this. 8 plus, let's say 4yi equals 5x minus 20i. And they're going to ask you to solve for x and y. Now it seems confusing when you look at this, but here's what you want to remember. We have a real part, and the real part is the part without the I. So the real part on this side is 8, and the real part on that side is 5x. And so that tells me those have to equal each other. So now we just divide by 5, so x equals 8/5. And then we take the imaginary part, the 4yi and the negative 20i, those also have to be equal. So you could write the I in, but it doesn't make any difference because we can divide by I. The only thing that's important is that the 4y has to equal the negative 20. And so now we divide by 4, so y equals negative 5, and that's how you solve those. All right, so your assignment on this is page 353, numbers 19 to 57, the odds, and 67 to 71, the odds. So make sure you're careful. That negative sign inside the square root, you're just going to pull it out and put an I in there, and that should take care of the radical and change it to an imaginary number so you can work with it. So a lot of it's completing the square just like we've been doing. Hopefully you'll find this helpful and easy to do.